Hello, Velociraptors, and welcome to my classroom. Up until this point, we've been throwing around the word chemical formula, or we've been looking at several chemical formulas in your course notes, but we haven't defined what the difference between an empirical formula and a molecular formula is. For this video, we're going to explain how to define both formulas and how you can use percent composition to find one or the other. Let's get started. So what do we mean by the difference in an empirical and a molecular formula? Well, let's take a look at some examples. So let's start with a molecular formula. A common example of a molecular formula that you're probably aware of is C6H12O6. And this has the common name of glucose. And you're probably aware of it from photosynthesis or cellular respiration in biology. Now, glucose, if you look at the molecule, each of the subscripts have a common factor. C6H12O6, 6, they have a common factor of 6. Which means it can be reduced. If I reduce this, I get the empirical formula, which is CH2O. Now, several molecular formulas can have the same empirical formula. So another example might be C2H4O2, which is just acetic acid or common vinegar. It also has the same empirical formula of CH2O. Another example might be CH2O. Itself has the same molecular and empirical formula, and in this case is formaldehyde. Now, I want you to also pay attention for two things here. One, all three have the same empirical formula, but they have very different properties. One's a sugar, one's a weak acid, and one's used to prevent tissue from decaying. So don't assume that even though they have the same empirical formula, that they have the same properties. The second thing that I want you to pay attention to is they're all composed of nonmetals. So I'm only reducing a molecule, meaning it's composed of nonmetals. If it's composed of a metal and a nonmetal, it's a formula unit, and formula units should already be simplified to their simplest form. We'll learn more about this when we learn about chemical bonding in Unit 4, but just to take note. Now, how can we use this in a problem? Well, let's take into account an application of this problem. We are a forensic scientist, and we've just appeared on a crime scene. Now, at this crime scene, we notice that there is a white powder available. We analyze this white powder and determine that it has the following percent composition. The question is, can we identify the unknown based upon its percent composition? Well, the compound has a 67.3% composition that's carbon, 7% hydrogen, 4.6% nitrogen, and 21.1% oxygen. Now, if you're not sure how percent composition, make sure that you've watched that video prior to this so you know what I'm talking about. Now, what we need to do to determine the identity of the unknown is we first need to convert these percents to mass. Let's just assume that percent doesn't exist. So if I'm just going to assume that carbon is 67.3 grams of carbon. And I want to convert that to moles of carbon. Now, we should already know that in order for it to go from mass to moles, I need to use molar mass. Well, the molar mass of carbon is 12.011. So 67.3 divided by 12.011 should get me that the number of moles of carbon is 5.6. And I need to do the same thing for hydrogen, nitrogen, and oxygen. So 7.0 divided by 1.008 is roughly about 7 moles. 4.6 divided by 14.007 is roughly 0.033 moles, and 21.1 divided by 15.9999 is 1.3 moles. This gets me a relationship between all of the elements contained within the molecule. Now, in order to find in relation to each other, well, how many carbons are there for every hydrogen or how many hydrogens per nitrogen, we're going to take the lowest amount of moles, in this case, nitrogen, 0.333, and divide it by every one of them. So I can get a ratio for how many of each of them there are per number of nitrogens. So I'm going to just do nitrogen first so that you can see. So the reason that it's this way is if I divide 0.33 by 0.33, I get 1. So there's 1 nitrogen for how many ever C, H's, and O's. Well, in order to figure out the other ones, I also need to divide them. So if I take C, 5.6 moles, and divide it by 0.33, I get that there's 17, which means that for every 1 nitrogen, there are 17 carbons. Now, I might also get that hydrogens here divided by 0.33, and I get that there are 21 of them. And lastly, I do oxygen and I get 4. So in relation to this compound or molecule, there are 17 carbons, 21 hydrogens, 1 nitrogen, and 4 oxygens. Note, if you divide by the smallest amount of moles here, and I get 17 and a half. I cannot have 17 and a half atoms of carbon. In order to cancel out a decimal place acquired here, you multiply by the reciprocal. So in this case, it's a half, so I need to multiply everything by 2. If I got a third, I would multiply everything by 3, and so on and so forth. So then you could get the correct molecular or empirical formula based on whole atoms. Now that means if I take this and convert it to a formula, then I would get that the formula for this compound is C17H21NO4. Now, what is C17H21NO4? Well, you might have already guessed it. It's cocaine. So in this case, my crime scene, I found cocaine. Let's look at another example, but in this case, we're not given the percent composition. We're actually given the empirical formula. So let's say I'm back at my crime scene and I locate a residue on some glassware that the perpetrator left behind. And I find out that the residue has an empirical formula of NaPO3 and a molar mass of 612 grams per mole. My question is, can you tell me what the molecular formula of the actual residue is? Well, in order to do this, I need to compare the two. So remember, the empirical formula is the smallest ratio of the two. So I need to figure out, is the molecular formula Na2P2O6, common factor of 2, is it a common factor of 3, Na3P3O9, or so on and so forth to the common factor. In order to figure out the common factor, I need to compare the empirical molar mass to the molecular molar mass. So if I calculate the empirical molar mass, I get that it's 101.96 grams per mole. To compare it, I'm just going to take 612 and divide it by 101.96, and I get 6, which means that's the common factor. So it is 6 times the empirical formula, which means that it's Na6P6O18. That's how we can use percent composition to determine unknowns and to convert an empirical formula in a molar mass to a molecular formula. Great work, Velociraptors. Now you understand how we can what the difference is between an empirical, the simplest form formula, and a molecular formula, the actual structural formula. And we know how to use percent composition to determine the empirical or molecular formula of an unknown. Great work. If you have any questions, please reach out to your instructor. Otherwise, thanks for tuning in.